Good afternoon, everyone, and thank you for joining me today with this webinar. My name is Mal Skoran, and I am a Program Associate for Green Energy Consumers Alliance. Before we get started, if you can hear me, just please let me know into the questions box. Just a simple "I can hear you" would be great. But just a little bit more about myself. I work mostly on our Drive Green program, which is an electric vehicle discount program, and I do mostly consumer education about electric vehicles. I'm excited to talk a little bit more about battery technology today because batteries are the crucial technology that will make electric vehicles accessible to all different kinds of consumers. So I'm excited to share what I know with you today. Before we get to that, let's just go over a few webinar logistics. First, everyone is muted to avoid background noise, but I encourage you to send me questions via chat, and we will have regular breaks for questions. So every couple of slides I can break and see what you all have to ask about the information. So let's get started. Green Energy Consumers Alliance is a nonprofit organization, and our mission is to harness our power as energy consumers to speed the transition to a low-carbon future. And Drive Green helps us accomplish this mission by getting electric cars on the road in place of gasoline-powered cars. EVs, or electric vehicles charged in New England, can cut emissions by 75% on a per-mile basis compared to gas-powered cars. And this is important because transportation accounts for about 40% of all climate warming emissions in New England, and light-duty cars, trucks, and SUVs make up the majority of the emissions from transportation. So if we can electrify our cars, we're taking a big step in the right direction to decarbonize that transportation sector. What's even better is that electric cars are as clean as the electricity used to charge them. So as state laws increase the amount of renewable energy required on the electrical grid, EVs will actually get cleaner every year. And on top of that, many communities in Massachusetts and Rhode Island are choosing to add even more renewable energy into their energy resource mixes, which is amplifying the environmental benefits of EVs even more. So if you're interested in that part of electric vehicles, I will be co-hosting another webinar on Tuesday, April 21st with Larry Cretion, the Executive Director of Green Energy Consumers, to talk more about the environmental benefits of electric cars and explain why EVs are greener than you probably think. So I encourage you to register for that webinar as well if you are interested in learning more about that. But the point is, electric vehicles are part of the green energy future, and lithium-ion batteries are a new, rapidly developing technology that will allow electric cars to replace gasoline cars. So this webinar is focused on the intersection of technology and economics for lithium-ion batteries. Here's our agenda for today. We'll be taking a deeper dive into the technology that makes electric cars possible. First, I'll discuss a little bit about the science of how batteries work, and then I'll move on to the challenges of developing the technology for electric vehicles and why producing batteries for these cars is harder than producing batteries than smartphones, for example. Considering those challenges, I'll talk a little bit more about the potential for market growth for batteries and what that means for the potential for EV adoption by consumers in the next decade. And as more people buy EVs, we'll have more batteries. So I'll talk about the possibility and end-of-life use for batteries, including both recycling and reuse. And then finally, I'll wrap up by taking a look ahead at what we can expect the industry to grow in the next couple of years. So I invite you to ask questions throughout the webinar, again, especially for clarity on the points that I've already made. But if you have a question about a specific topic that I've listed here that I haven't reached yet, recycling, for example, then please hold on to it until we get to that section because it's likely that I answer your question in a later slide. So with that, let's get started. Lithium-ion batteries will be the focus on this webinar since that is the chemistry that dominates the EV industry. But in general, batteries all kind of operate on the same principle. You're using a voltage difference between positive and negative terminals of the battery to drive a flow of electrons. And that's the electricity that we can use to power a device attached to the battery. So a battery basically takes advantage of a principle that you might remember from physics class in high school, which is that opposites attract. When electrons flow in one direction, some sort of positive ion has to flow and balance that negative charge. So what do I mean by that? Well, in the diagram, you can see a big V at the top there, and that V can be either a power source if you're charging, or a load that you can discharge to. So when you attach a power source to the battery for charging, electrons are forced to flow towards the negative part of the battery. But positive and negatives attract, so the lithium ions follow the electrons into the negative part of the battery too. So they actually leave the metal oxide, which is the bluish crystal-like shape on the left, and enter into the layers of graphite on the right that make up the negative side of the battery. Notice that the ions can't pass through the wire where the electrons flow, so they flow in the middle there in a fluid called an electrolyte that allows them to easily go between the positive and negative sides of the battery. And in this graphic, the gray circles are the lithium ions. So you can see here they're about evenly distributed between the positive and negative sides of the battery, which means that in theory, this battery would be charged to about 50%. So for me, it's a little easier to visualize and conceptualize that. And then when you disconnect from the power source, all the ions stay put. It's not until you need power, let's say, to drive your electric car, that the positive ions are allowed to flow back into the positive side of the battery. And that pushes electrons back to the positive side of the battery as well. And that flow of electrons is the electricity used to power the motor in your electric car. And the motor in an electric car is basically a rotating magnet. It's an induction motor. So the more current you deliver from the battery, the faster you drive. It's a pretty simple type of motor compared to gas-powered cars. So that's the general idea for how batteries work. In a lithium-ion battery, it's lithium ions that are flowing, but in other types of batteries, so for example, AA or AAA batteries, you might be using zinc ions instead. So that chemistry can vary depending on the type of battery it is. And there are tons of different types of batteries, but lithium-ion has really dominated the EV industry so far. But even within lithium-ion, you can have other metals in the positive side of the battery that will change its overall performance. So most of the research for developing better lithium-ion batteries is focused on optimizing the ratio of metals in that positive side of the battery. This is important because lithium-ion batteries have a lot of performance criteria that they need to check off to be good enough to be used in cars. So for example, EV batteries need to have good energy and power density. That is, they need to be able to store a lot of energy and weigh as little as possible. There's also a volume constraint. These batteries need to be slim and take up less physical space in the car so that you can actually fit more of them into the car. If you can store a lot of energy in the battery, that's what's extending the driving range of the vehicle and making it more valuable to consumers. So that's why adding other metals is important. So for example, nickel, which is a metal that is often used in lithium-ion batteries, helps deliver that high energy density. So what it does, it provides a really good crystal structure for more of the lithium ions to be able to squeeze into that positive side of the battery. And so it increases the battery's overall capacity. Lifespan is important also. Automakers want to use these batteries for a long time and have them be reliable under high duty usage. As a counterexample, cell phone batteries are decent, but they're also built with the understanding that phones just don't use that much energy, and people are likely to replace their phone when it's obsolete in 2 or 3 years. Cars are driven for an average of 11 years in the United States. So making sure that these batteries are reliable and last a long time is very critical for the industry right now. Safety is another important factor. A couple of years ago, you might remember that there were Samsung phones with a certain type of lithium-ion battery, and those are actually catching fire in airplanes. So you want to make sure that these batteries don't produce too much excess heat, which could trigger a chain reaction that leads to fire. And there are dozens of other considerations like this to design the battery around, including recycling potential, charging efficiency, consistency and voltage output, and lots of other things that you might not think about as a consumer, but are really important for the overall performance of the battery. But the problem is, if you try and optimize a battery for one thing, like energy density, it's usually at the expense of something else, like cost. So researchers are really playing this balancing game to try and figure out which combinations of materials create the best characteristics for the application of electric cars. And all this research into lithium-ion batteries is improving the technology really quickly, which is good because there are more applications for energy storage than ever before. So as an example, here are two common types of lithium-ion battery, which have very different use cases. So LFP, or lithium iron phosphate, is a type of lithium-ion battery that has iron and phosphate in the cathode. It's a stable battery with a long lifespan, but it's just not very energy dense compared to other types of chemistries for the battery. And if you're talking about a car, that's a deal breaker, because cars need to be as lightweight as possible for efficiency reasons. So if you have a really heavy battery, you start to have diminishing returns on the energy that you can store in it, because the car is running less efficiently, lugging that heavy battery around. But if the application is a grid scale storage for electricity to store energy that is being produced from wind turbines, for example, then energy density is less of a critical design factor. So improved lithium-ion technology is really making this kind of storage financially possible. Because with really cheap batteries, you can pair a wind turbine or a solar farm to it, and then you have energy when the wind isn't blowing or the sun isn't shining, which is a very, very new idea in terms of grid management. Cheap batteries also mean that this kind of arrangement could be cheaper than natural gas power plants that ramp up or down sometime in the future. And I'll talk a little bit more about this when I talk about potential cases for battery reuse. But NMC, or nickel manganese cobalt oxide, is another type of battery chemistry that seems to be more well-rounded, and that is the industry standard for electric cars right now. So you can see in the photo, there's an image of an actual battery pack in the floor of the car. So depending on the nickel to manganese to cobalt ratio in the battery, you'll have different performance as well. So NMC 811 is 80% nickel, 10% cobalt, and 10% manganese. And that is really the cutting edge of EV battery technology right now. Tesla is using NCA, which is a nickel cobalt aluminum mix. And this uses more cobalt and less nickel than NMC, which is what most other car makers are using, and also aluminum, which is pretty cheap and very abundant compared to a lot of the other metals. So Tesla is claiming that these batteries can charge faster, they have better longevity and lower costs as well. So we may see a transition to this other chemistry being the industry standard. But the important thing to note is that this is all in flux, and there is a lag between batteries that work well in a laboratory and batteries that are inexpensive and easy to manufacture. And it can take some time to transition from the lab to something that is scalable to be put in cars all over the world. As an example, lots of people are excited about solid-state batteries, which would replace the liquid electrolyte in the battery with a solid material, improving both safety and energy density. And while it has been shown to work in some research labs, it can take a long time for this technology to scale up to the point that it's the industry standard. So as a result, it could be about 10 years before we see some of these solid-state lithium-ion batteries take hold in consumer products. But you might see news all the time about different breakthroughs, which is great, but it takes a long time for the industry to change. So next, I'll be talking about how batteries will affect electric vehicle adoption. But first, let's take a quick break for questions. Okay, I don't seem to see any so far. Just a lot of people telling me that they can hear me, which is good. Someone asks, what was the technology you mentioned after NMC? So I believe I said NCA, which is nickel, cobalt, aluminum, and that is the technology that Tesla is focusing on currently. Okay. So if there are no more questions, then I will move on. So now that we know a little bit about how they work and what the challenges are, let's move on to talking about how battery costs affect the overall cost of an electric vehicle. So upfront cost is one of the biggest barriers towards EV adoption for consumers. Even though there are financial incentives available on the federal level and in many states in order to help people buy electric cars, the sticker price can still discourage a lot of shoppers. So EVs really need to be able to get cheaper to effectively replace all, if not most, gas guzzlers on the road. And the battery, far and away, is the most complicated and expensive part of an electric vehicle. The induction motor that drives the electric car and makes the wheels turn only has about 20 moving parts compared to an internal combustion engine that can have upwards of 400 moving parts. So in a lot of ways, electric cars are simpler machines than the gas-powered cars they're replacing because they don't have catalytic converters or pistons or fuel injectors or any of those parts like in a gas car. And that's a big reason as to why electric cars cost less to maintain than gas cars. But it's the battery that makes the car expensive to purchase upfront. Currently, batteries account for a little over a third of the total purchase price of a new electric car, which is quite substantial. The good news is that batteries are getting cheaper and very quickly, in fact. In the first graph, you can see that since 2010, lithium-ion batteries have dropped steadily to nearly 85%. And in that same time frame, we went from almost no electric cars on the road to over 1 million. So you can see battery prices and EV adoption rates are intimately connected. And since 2011, EVs have been expanding beyond their niche market and really entering the mainstream. And in 2019, we saw an additional 21% drop in prices compared to 2018, which continues to be consistent with the trend that we're seeing. So it doesn't look like things are slowing down. And again, there are just over 1 million EVs on the road in the United States. But still, EV sales represent just under 2% of the total number of cars sold in the US market in 2019. So the takeaway here is that people have responded to lower prices, and cheaper EVs means that they will replace gas-powered cars. It's just a matter of when. So let's look ahead. When do experts think that electric cars can really give gas cars a run for their money? Well, for more people to buy electric cars, they need to be about the same sticker price as comparable gas cars. So the target price for battery packs to make electric cars competitive with gas cars is about $100 per kilowatt hour. And that's for the entire pack itself. We're about $139 per kilowatt hour now. So we are close to that target where electric cars will actually become cheaper. And experts expect to meet this target by about mid-decade, so let's say 2025 or so. And our historical trends show that that'll really encourage people to switch to EVs, because at that point, they will not just be less expensive to fuel and maintain, but cheaper to buy as well. And for most people, it'll just be an economic decision, not even an environmental decision. It'll be a no-brainer. And so for that reason, by 2025, some experts say that 30% of new car sales will be electric vehicles. And if you're skeptical about this prediction, that's fair. It is an aggressive prediction, and it makes assumptions that the technology will continue to improve at a fast rate and that consumers will be responsive to this disruption in the car buying market. But in general, disruptive technologies spread really quickly, even when they're replacing an older, more established technology. In this graph, and I promise it's the last one I'll show you, you can see how different technologies quickly go from less than 10% adoption all the way up to 80 or 90% to dominate an entire industry. And you can see this pattern with all different kinds of new technologies. So as an example, my first cell phone was a Motorola Razr. At the time, I thought it was the coolest thing ever, especially because the very idea of cell phones was still pretty new. And then a couple of years later, the iPhone came out, and as soon as I could, that's what I switched to. And pretty quickly, that's what everyone else had also, or other types of smartphones as well. The point there is that it can take as much time to go from 0% adoption to 2% as much to go from 3% to 80%. And that tends to be the pattern that we see with new technologies. And you'll see that as we move forward in time, it actually is taking less and less time for technologies to enter the mainstream when they're new. So just consider that the smartphone integrated itself more rapidly in our lives than the telephone did when it was first invented. So it's really, the pace of technology improvement is increasing really quickly. And it's not crazy to think that EV adoption could go this route, especially when EVs become as cheap or cheaper to buy than gas cars. If you're interested in learning more about this, there's a tech analyst named Tony Seba who studies disruptive technologies, and he's an expert in this field and has a lot of interesting things to say about how quickly EVs will become the norm. But if we do consider this prediction to be true, we can expect around 8.4 million cars to be electric in the next 6 years, which is substantial. And if that's a little too abstract for you, it's easy to see the pattern via Nissan LEAF prices. So the LEAF is one of the oldest EV models. It was released in 2012, and every couple of years, prices either decrease or range improves, both of which are directly connected to battery prices that we saw historically dropping over the last decade. So specifically between 2014 and 2018, range effectively doubled while the car's price stayed pretty much the same. So in other words, battery pack prices fell significantly so that the LEAF had a much longer range without much more additional cost. And as batteries improve, you can travel much further and pay less to be able to have that higher performance battery. And so that's really the crux of the issue, is trying to find a price point where consumers will buy these cars, but also at a range that's practical. So these two factors pretty exclusively are controlled by the lithium-ion technology and how good it is. So let's just take a step back. Why are EV batteries so expensive now? because seemingly we have plenty of lithium-ion batteries because of laptops and smartphones and e-readers and tablets and all of those devices that are widely integrated into our lives that rely on the same technology. So first, the battery capacity of these devices is very tiny compared to what EVs need. So the entire industry, including battery manufacturers and raw materials mining, need to be scaled up dramatically to increase supply. And that just takes time, even though the industry already exists. So consider the fact that it takes about 1 kilowatt hour to charge a smartphone for a year, compared to 3,000 kilowatt hours to drive 12,000 miles a year, which is the average. So it's just a much higher energy demand. The second reason is that the supply chain is not developed yet. So there's really very little connection between the automotive industry and the battery industry historically, because they've never had to work closely together before. Car makers have always controlled how many cars they can produce because they're making almost everything in-house. But now all of a sudden it's out of their hands because they don't manufacture batteries. So EV development really depends on those partnerships between traditional automakers and the battery manufacturers, so like LG or Panasonic and those companies. Then finally, the raw materials for lithium-ion batteries are pricey. Cobalt, lithium, and nickel, which are the main metals to think about when you're talking about lithium-ion batteries, are in good supply, but they're expensive and they're only found in certain parts of the world. And so just trying to decrease the cost of those will take some time. But the good news is that all of these barriers can and will be addressed. So why are these batteries getting cheaper? The electric motor, as I mentioned, only has about 20 moving parts compared to internal combustion engine with about 400 moving parts. So it's already less expensive to manufacture an electric car because of that simplicity. So savings in the car's parts and labor can be offset against the high battery and development cost for automakers. The second important factor is the economies of scale. So the more units that you produce, the less it costs to produce each unit. And so not only are automakers increasing their ability to build these cars, but battery producers are increasing their capacity to manufacture the packs, and mines are churning out metals to increase their capacity also. So pretty much every part of the supply chain is building out. And you can see that in worldwide manufacturing for lithium ion, which tripled in the last 5 years. There's also research to decrease the use of these expensive metals so that we can save on production costs without losing out on performance. So the more that we can reduce the use of the expensive metals and try to find cost-effective alternatives, the cheaper the batteries will be. And as an example, finding a way to use more aluminum, which is about 10 to 50 times less expensive than some of the other metals as a comparison, would be a substantial improvement. And so that, I think, is part of Tesla's idea in using that NCA battery, which has the nickel, cobalt, aluminum mix instead of some of the other battery chemistries that are out there. So, as a recap, batteries are getting cheaper, and by mid-decade, they will probably make electric cars less expensive to buy than combustion engine cars. That will drive demand for electric vehicles to be much higher, as consumers will be attracted to lower purchase prices and all of the other benefits of driving on electricity. And so we want to rapidly increase lithium-ion production in order to meet this demand. So next, I'll be talking about raw materials and recycling, which is a topic of interest for many people who want to make sure that electric vehicles really are as green as they seem. But first, let me take another break for questions. Someone is asking between the cost difference between NMC and NMA. The cost difference between different lithium-ion batteries is kind of hard to determine because we're looking at industry averages. And so, for example, it can be hard to compare one manufacturer that's producing a certain type of battery really cheaply if all of their competitors are not able to offer those same prices. So it's unclear exactly what the cost difference is there. I'm sure someone kind of deeper into the industry would be able to give a more robust answer to that, but not quite sure there. I can get back to you about that after the webinar. Someone asked, do you think solid-state batteries will eventually become the standard battery? So I think that eventually, yes, it is very possible that solid-state batteries replace the lithium-ion technology that we see now, just because that seems to be a focus of a lot of research. And it's just a matter of scaling that battery up in order to meet the demand of lithium-ion batteries across the globe for electric cars. It's tough to say though, because I do think that will take at least 10 years. And, with the way that technology is moving, it's very possible that, in 20 years, we're using a battery technology that is totally different from lithium ion, and it's, a very different chemistry, and it's better than the technology that we have now. But it's just it's hard to make those predictions. So solid state would be a dramatic improvement to what we have now, because instead of having that liquid electrolyte, which is heavy and takes up a lot of space, you could have either glass or some type of polymer that takes up less space while kind of having similar performance. So you can actually fit more batteries into a smaller area. So that would be a dramatic improvement, and I hope to see that in the next decade or so. Someone asks about data including plug-in hybrids. So what is my view of the market for plug-in hybrids looking forward? So that's a great question. So it's pretty clear that a lot of automakers are moving forward with the fully electric cars. And the reason for that is just a lot of people have considered plug-in hybrids to be kind of like a stepping stone technology, right? A way for people to kind of get used to driving an electric car and get some of the benefits of driving on electricity while still having that gas backup as security. But most of the commitments that have come from automakers are, focused on all electric models. So in particular, I know that GM is planning on releasing an entire line of all electric vehicles for all of its different brand names. So Chevy has several coming up by mid-decade. I believe there's going to be an all-electric Cadillac. You might have seen during the Super Bowl commercials, there's an all-electric Hummer that's coming out. So the focus is really on all electric cars, and I do not see a bright future for plug-in hybrids moving forward. I own one myself. I think they're great, but the cost effectiveness of electric vehicles as it improves, it really will just make more sense to go with the all electric cars. Someone is asking that that they've heard the cost of the Bolt exceeds its sticker price. Is this why GM doesn't advertise the Bolt? Yes, absolutely. So because electric cars are a totally different technology than what automakers are used to producing, It has taken a lot of research and development dollars for automakers to try and produce consumer-friendly electric cars. And so the cost of the bolt does exceed its sticker price. What GM is betting on, however, is that the market will transform to favor electric cars over gas-powered cars. And so all automakers right now are trying to find a good balance of developing their supply chains and getting ready to ramp up electric vehicle production while continuing to sell the combustion engine cars that make them the money that allow them to continue this development. So some automakers are kind of taking the charge ahead, no pun intended, more than others. So Volkswagen, for example, has committed to an all-electric fleet at some point later this decade. And then there are other automakers, Toyota comes to mind, that they really bet on fuel cell vehicles as the next technology. And so they've been a little slower to announce their plans for electric vehicles. But definitely all automakers are kind of hedging their bets as to when this transformation will happen. And they definitely don't want to be caught flat-footed and unprepared because, it's kind of, it'll be a survival of the fittest for sure. Someone asked about the environmentally destructive mining regarding lithium, cobalt, and nickel. So I will use that as an opportunity to go ahead and discuss the next part that I've prepared. And I do see some additional questions, and I'll try and get to them at the end if we have time. But moving along. So I've already talked about how using fewer expensive metals will make batteries less expensive, because not only is there an economic incentive to remove these expensive metals, there's an environmental and human rights incentive as well. And I mention this because it's a question a lot of people have about batteries, So in general, manufacturing an electric car, including battery manufacturing, is actually more emissions intensive than manufacturing a gasoline car. So of course, once the cars get on the road, the EVs have a lifetime emission rate that is lower than gas cars. So if we can minimize the environmental impact of mining for these metals, then we can further reduce the impact that these cars have on climate and the other environmental impacts as well. So because of the differences in how each metal is mined, the challenge of each one is unique. So in Chile, on the left image there, mining lithium requires a lot of water. And lithium is found in the Atacama Desert, which doesn't have a lot of water. So managing supplies there is a real challenge. And water insecurity is the main problem there. Presenting a totally different issue is cobalt. The mining is artisanal, so people go out and basically pan for it, like prospectors would look for gold during the gold rush. But when people do this, they're exposed to unsafe conditions in the process. And so because there aren't good labor laws in the Democratic Republic of the Congo, workers are not in good condition. And that's where about 60% of the worldwide supply of cobalt comes from. And these are issues that exist because of our existing dependence on lithium-ion batteries. And so economic pressure will hopefully alleviate some of these issues and reduce our dependence on mining. And so one potential way to do this would be recycling. People ask about recycling as a way to both minimize the environmental impacts of metal mining and to lower the cost to produce new batteries in the future, which is a great idea. And this is a developing market, but there are essentially 3 barriers to overcome to allow widespread lithium-ion battery recycling, which is the actual process and the supply chain aspect of it, the regulations to make it possible, and the financial viability of it. So first, let's talk about the technological challenges of recycling itself. Here we have a breakdown of a typical NCA battery, which is the nickel, cobalt, aluminum mix, which is what Tesla uses, and the materials within it. So you'll notice that there are a lot of different metals and other materials, and this complexity in the battery complicates the recycling process. So smelting is the process of melting the dead battery down and then extracting metals from it, where you're basically using the different melting points of each metal to separate them. But this process is energy intensive and expensive, and also not everything can be smelted. So you can recover cobalt, nickel, and copper, but not lithium, aluminum, or the carbon in the battery. Those are all burned up in the process, and there are toxic byproducts that need to be managed with that as well. So you can't recover everything and make a brand new battery right away. There are other recycling methods being developed, but it's hard to make any process profitable using batteries right now. And that's because for the recycling business model to work, you need a large feedstock of dead batteries flowing in. That requires a pretty sophisticated collection process to centralize all of these batteries in one place, which is a big barrier for regulation to hopefully address. But it's also difficult to scale battery recycling when car makers are trying to make their batteries last as long as possible. EV manufacturers are facing pressure to make batteries last as long as possible and make consumers comfortable with the technology. And so that means 1,000 units produced today won't mean 1,000 units coming back in 5 years, which is crucial for developing a recycling process that is profitable and financially viable. And also, because the EV industry is so young, many of the batteries are in EVs currently, so there's nothing to recycle just yet, and there's nowhere for the industry to be growing right now, so we just don't see a lot of activity here. There's definitely some, but it's just still kind of in its early stages. And with all the different battery chemistries and all the ways that battery packs are assembled, the process would have to be a little different for each battery. And there's no standardization across different manufacturers. So because battery chemistry is changing all the time, it's a chicken and egg problem. You know, there's no economic model for large scale recycling. And because of that, battery producers are not focused on improving recyclability. So we see some of these barriers just because the market is so new. But that's why we need regulation. Currently, less than 5% of lithium-ion batteries are recycled in the borders of the United States, compared to nearly 100% of lead-acid batteries, because that's what the law says. It's the law to prevent environmental damage. In terms of worldwide recycling, about 50% of lithium-ion batteries are recycled globally because both the United States and Europe ship them out to China to deal with. So there should probably be more refined regulation there to support the development of the industry domestically. And ironically, reusing batteries here in the US will help keep those batteries within our borders, which will help develop the recycling industry. And I'll be talking a little bit more about reuse in the next few minutes. But really, the biggest barrier for recycling is the economics. Batteries are just too valuable once they've already been assembled to make the recycling worth it. So you're actually diminishing the value of the battery by taking it apart before it's totally dead. Another way of thinking about it is this. Recycling materials may end up being less expensive than going out and mining for new materials. But if it's more profitable to go ahead and reuse the batteries after a car's useful life is over, then that's what will happen. And so recycling makes sense as a final destination after potentially multiple uses after a battery has been removed from a car. And as a point of hope for the industry, in the past, recycling was used as a way to comply with laws. And now it's a way to get valuable materials back in the face of shortages. So that additional economic pressure will help it move forward once we have kind of a steadier rate of EV adoption. So if batteries continue to be valuable at the end of their useful lives in cars, where will they be used? And part of the reason we want to think about reuse is because these batteries are built to last. They lose capacity to hold charge little by little over a long period of time. You might have seen this behavior with your smartphone. It might not last as long before needing to be recharged as when it was new, but it still works pretty well. And EV batteries are even more reliable. So the degradation is caused by cycling. So charging up to 100% and then draining down to 0%. And that comes with age. So charging and recharging generates heat within the battery, especially in the bottom 20% and top 100% of the capacity. So the more you charge and recharge, the more you'll see this capacity fade. And this is just a physical reality of these batteries. But the good news is that they last the life of the car easily. So you can see in this graph here, it shows an average degradation of vehicles of 6,000 different data points over a long period of time, over 6 years. So in that 6 years, the average EV only loses about 10% of its battery capacity, which for a 250-mile range EV, that's just 4 miles of range loss a year, which is barely noticeable if you're a driver. But importantly, a battery is considered to be significantly degraded if it's lost about 20% of its original storage capacity. So if your 60 kilowatt-hour battery is all of a sudden acting like a 48 kilowatt-hour battery after 6 or 7 years of use, that's not great for your car. You might want to trade it in at that point. But there's still a lot of significant battery capacity that could be used for something else. And so that's where the potential for reuse comes in. And this will be effective even if the recycling stream is not developed. So if you are interested in EV but are concerned about battery health, don't be. Batteries easily outlast the life of the car. And if not, there are warranties in place for 8 years or 100,000 miles worth of driving to protect you as a consumer. So even after a battery is done being used in your car, after years of driving, it can be used for something else. And we're already actually seeing this with the existing lithium-ion batteries that we have. So old laptop batteries often end up in those small power banks that you can use to charge cell phones or other mobile devices. So that's already happening. But EV batteries have a lot more storage to be reused for higher duty tasks and encourage the availability of cheap and abundant storage. So as I mentioned previously, grid storage will be especially important to support renewables. Since electric cars are powered by energy from the grid, more renewables will mean cleaner running in electric cars. But because solar and wind are non-dispatchable, meaning that we can't control the amount of wind that we have or the amount of sun that's shining to generate the power we need at a given moment, we need a way to store energy from renewables for the grid to be used later. So why not rely on these used electric car batteries to meet this storage demand? It's kind of a match made in heaven, and it is the direction that we're going in. So Daimler, the German automaker that manufactures Mercedes-Benz, took used battery modules and turned it into a stationary storage project as a kind of proof of concept. So the energy stored in these batteries feeds back into the German grid at a power capacity of about 9 megawatts. So it's pretty substantial. And this doesn't have to be grid scale necessarily. It could be on the scale of homes to be paired with solar as well. So you as a consumer could one day choose to repurpose an old car battery to use as backup storage for your home. It just kind of makes sense. We're just waiting for the business models to pop up and facilitate this process. And there are just so many potential reuse applications for these batteries. There's also a project that powers streetlights in Japan with used Nissan LEAF batteries. So what they did is they paired a solar panel, a battery, and an LED all coupled together. So, these have existed for a long time, but now paired with a used car battery just makes it that much more economical. So you're really getting the full use out of the manufactured battery. And this kind of off-grid streetlight would be completely disconnected from the electrical grid. So in the case of an outage, there would still be light. So these kinds of projects can contribute to resiliency, which is especially important with the rising threat of natural disasters in many areas of the world. Returning to the question of electric cars, or the topic of electric cars, I said to expect about 8 million EVs on the road just in the United States by 2025. So you have car manufacturers, battery manufacturers, miners, all of these stakeholders, each of which need to scale up drastically to meet demand. So car makers all of a sudden are not in control of how many vehicles they can produce because there are a lot of places where a kink in the supply chain means that not as many cars are built. And I'm sure many of you are familiar with the slow rollout of the Tesla Model 3. And they just could not produce enough cars to meet the demand and all the pre-orders that had been filed. But it does prove that there are a lot of moving pieces that have to be working together to create an effective supply chain for EVs. So Tesla's Gigafactory is an attempt to circumvent the difficulties of the supply chain economics and try to meet the demand for batteries. So it's basically a Panasonic factory, but it's owned by Tesla specifically to make batteries for their cars. In theory, they had about a 35 gigawatt-hour per year capacity, but in its first year of operation, the Gigafactory only achieved around 2/3 of that, which is why Tesla failed to deliver as many Model 3s as they thought they could earlier that year. But this problem is not unique to Tesla. Battery manufacturers have to scale up very quickly in order to meet demand. So there are partnerships between automakers and battery producers because both of them want to lock down supply. So as an example, Volkswagen, which did make their commitment of having an all-electric lineup of cars, is working with an unnamed partner and spending $1 billion to produce battery packs near its headquarters in Germany. And so that is fairly new and is not shown on this map here. But this map is useful in seeing how much battery production has grown in these last couple years. So the black little battery packs are the 2016 capacity, and green is capacity in 2020. So again, there are more factories on the way, especially in the United States and China. And only a handful of these battery producers can meet the demand that is coming. And a lot of those batteries will come from China. So that reflects their very aggressive moves towards dominating the industry. They have some of the most aggressive EV purchase incentives in the world to improve their air quality. And they're receiving a lot of the dead lithium-ion batteries to be recycled too. So they're really setting themselves up to dominate every part of the industry. And there are several Chinese versions of Tesla, that is automakers that are specializing in electric vehicles. So BYD is one such example. They're producing batteries to go into their electric buses and cars, and creating cars with mass appeal for the average consumer. And there are about 9 such companies with the same business model. And while not all of them will be successful and all of them are only selling cars in China, it is making the country full of resources and assets for development. And note, there is an LG Chem plant that is going to be built in Michigan, which you can see on this map. There will also likely be another one in Kentucky or Tennessee to deliver batteries for Fiat Chrysler and Volvo, but maybe also GM, Hyundai, and Volkswagen. And LG Chem already delivers batteries for the Chevy Bolt. So in the near future, this sector will explode, and there is a lot of room for growth here. So we've covered a lot of information here. I'll be sending a recording out with the slides to everyone who registered. I do want to take a look at the last couple of questions with the last few minutes that we have. But feel free to share this information widely. And let me see what other questions I have here. And any questions that I don't get to, I will definitely try and get to them via email as well. Okay, this is a great question. What are good practices to keep my new EV battery at top condition? So one tip that I can give you right now that will be especially useful if you are working from home because of the stay-at-home orders that are in place for most areas of the country. Trying to keep your battery around 50% when it's being stored and not driven for a long time is a pretty good thing to do. As I mentioned earlier, batteries generate the most heat when they're close to 0% or close to 100% charged. So keeping it around 50% will keep the battery happy if it's not being driven very much. And that's probably the best tip, and I can send some more along after the webinar is over. Someone asks, in some countries, the government pays 50% of the cost of EVs. Why is the US so lame and only gives a tax credit, which is really only usable by the affluent who can afford an EV anyway? Oh man, that is a great question. So definitely there has been a lot of leadership in other countries to reduce the cost of purchasing an EV, and also, adding additional benefits to EV drivers. So one state that has been really good about this is California. In addition to offering incentives for things like charging and putting a lot of public infrastructure money to developing charging networks, California has this great program that allows EV drivers to have access to the carpool lane. So even if you're one driver in a car, if you're in EV, you have access to that faster lane. So there are a lot of kind of small policy decisions that states are choosing to employ in order to encourage more people to purchase electric cars. I do wish we saw more of that kind of effort across the United States. But yeah, I don't know what to tell you. I wish the policy was stronger. But as a point of optimism, these cars will be getting cheaper, and so in just a couple of years, the technology will be accessible to all sorts of consumers. And the pre-owned market is already making the technology accessible to more folks. I bought my electric car, my plug-in hybrid pre-owned, which is not something, I wouldn't have been able to purchase a brand new electric car with my budget. So there are options, and hopefully the improvement of technology means that more people can take advantage of it as soon as possible. But yeah, there are some countries and some states are better than others for sure. Okay, there are still a couple of questions which I will be happy to answer via email, so definitely be on the lookout for that. Since it is 1:02, I don't want to take up more of your time today. So I will definitely follow up with you on those questions. But thank you again for joining me this afternoon. I had a lot of fun delivering this webinar, and I hope you all were able to learn something. And please don't hesitate to reach out to me via email if you continue to have questions, or if you think of something later. I'd be happy to answer that for you. So thanks again for joining me, and I hope you all enjoy the rest of your afternoon.